When we graph functions, we do it on the Cartesian plane. The Cartesian plane is basically just the two-dimensional plane along with a way of describing points in the plane. So we describe a point on the plane using an ordered pair of coordinates where the first coordinate represents how far to the right or to the left we travel, depending on if that coordinate is positive or negative, and then the second coordinate is how far we travel up or down, depending on if it's positive or negative, respectively. So 4 comma 2, we go right 4 and up 2. Negative 2, positive 3, we go left 2, up 3. 1, negative 4, we go right 1, down 4. And then negative 5, negative 1, we go left 5, left, and down 1. So remember that we can describe a function using a graph as follows. So we just draw some curve, could be like any curve or whatever, on our Cartesian plane, and we represent our, or we use our horizontal axis to represent our inputs. So we can like sort of label inputs on that axis, and then our vertical axis will represent outputs. Sometimes your inputs don't have to be numbers, but in most situations they will represent numbers. When they do represent numbers, you want them to be evenly spaced apart. Like you don't want them to go like 1, 2, 4, 8, 16, 32 or something like that. You want everything to be to scale if possible. You read this as like, so this point on the graph is 6 comma 5, and so that would mean that your input is 6 for the function and 5 is your output for the function. So this reads as f of 6 is equal to 5. And also over here, the point 0 comma 2 is on the graph. Therefore, that would tell you that f of 0 is equal to 2. So one question you might ask is like, does this work for like any curve that I would draw on the Cartesian plane? And the answer is no, and a way of checking that is the vertical line test. So if you just draw any curve in the Cartesian plane, and you say that your horizontal axis represents your inputs, and then your vertical axis represents your outputs, as is standard. The vertical line test says that if you are able to draw a line that passes through the graph in more than one point, so here this is passing through in 3 points, then it would fail the vertical line test and not represent a function. The way that you can see why that is true is as follows. So here I have some points labeled, so my horizontal axis is, my inputs are labeled by x. And this right here corresponds to an x value of 7. This line right here is literally defined to be the line x equals 7, because the x coordinate is 7 for all of the points on this line, and that is all of those possible points. Anyway, so if you look at these points on the graph, the Cartesian coordinates would be 7 comma 6, 7 comma 2, and 7 comma negative 2. And therefore this would tell you that f of 7 is equal to 6, f of 7 is equal to 2, and f of 7 is equal to negative 2. And so there's a problem with that, because remember the defining characteristic of a function is that each input has a unique output. Okay, so the input of 7 is equal to 6, 2, and negative 2. So you're getting out like 3 possible answers for that, and so this would not define a function because you don't have a well-defined value for f of 7. You want to plug in 7 and only get one possible value out. Okay, let's look at some examples of functions. Linear functions is probably the most basic of examples, and they are very common. And sort of the reason that they have their name is because if you look at their graph is just a line. So here's just a line, you can characterize these in other ways as well. So lines just have a constant slope. So if you were to take any 2 points on this line and then compute the slope between those 2 points. Slope is rise over run. That slope, no matter which 2 points you calculate that slope for, you're always going to be getting the same thing. This rephrased slightly differently in a way that's more useful for contextual problems or like word problems is that linear functions have a constant rate of change. Okay, so the rate of change of the function, which is basically the same thing as the slope, is going to be constant. And the last way that you could categorize them is, well, the function is going to have the form f of x equals mx plus b. You could do like ax plus b or whatever. This is just more standard for whatever reason. M represents the slope or the constant rate of change of the function, and b is the vertical intercept. If you were to plug in x equals 0 to this, you would get f of 0 is equal to m times 0 plus b, which is just b, so that's why that's right there. And let's do an example with this. The Math Center is selling temporary tattoos for $2 a pop. They had to pay $32 to get the tattoos beforehand, and we want to know like what's the formula for the profit after selling n tattoos, and then maybe we can graph this after. Okay. So the profit. So they're selling them for $2 per tattoo, and so if they're selling 5 tattoos, they would make 2 times $5. If they're selling 7 tattoos, it'd be 2 times 7. And if they're selling n tattoos, it would be 2 times n. So they're going to get that many dollars. But they had to pay $32 to get the tattoo first, to get the tattoos. And so whatever their revenue is, this is like their income, you have to take away 32 to get their overall profit. Right? This is like your income minus your outcome that you had to like pay to start. And so if we wanted to graph this, it's usually good to start with your vertical intercept. Oops. So p of 0 is equal to negative 32, and so this point right here would be on the graph, negative 0 comma negative 32. And then the slope is going to be 2. So every increase of every increase of 1 in your input, your output is going to go up by 2. Here my inputs, or my scale is like going up by 8s. So because the slope is constant, if I go up by 8, or if I go over by 8, then I should go up by 2 times 8, right? The slope is 2, so if I do like 16 over 8, that's like equivalent. So I go over 8 and up 16, over 8, up 16, over 8, up 16. And so you can see that this will be a good, accurate graph of our function. This right here, this is our horizontal intercept. This is our vertical intercept. It's where it intersects the vertical axis. This is where it intersects the horizontal axis. If you were to plug 16 in to this function, you would get out a 0. Yeah, so that's that. All right, last one. A ball is thrown off a building. Its height in feet after t seconds is given by this formula right here. H of t equals negative 2t squared plus 12t plus 50. When you throw a ball like up and off a building, it's going to just follow this arcing trajectory. And the graph is basically just going to take those heights and just graph them over time. So you might not get like the exact same trajectory curve over here, depending on like, you might throw it up like here or throw it here, and you'll still get like the same graph or whatever. But not really too important. But effectively, this graph is going to look very similar to this this arc that you're throwing the ball off the building for. And so this is an example of a quadratic function. Quadratic functions, in the same way that linear functions look like ax plus b or mx plus b or whatever, here you have like this extra squared term, this like x squared term right here. So quadratic functions look like ax squared plus bx plus c, kind of like up here. And another defining characteristic, with linear functions, they had a constant rate of change, and with quadratic functions, they have a constant acceleration. So in this example up here, the constant acceleration is literally just the force of gravity. So the force of gravity is just constantly pulling your ball down. So even though you threw it up, the velocity is like upwards at the start. Gravity is still accelerating that that ball downwards. So the ball is still accelerating downwards throughout the entirety of this trajectory. So it has a constant acceleration, just given by the force of gravity. So here's an example: x squared minus 4x plus 4. You could plot these points in a table. So anytime that you don't know how to graph a function, you can just set up a table and plug in a bunch of values for it until you sort of have a good feel for what the function is going to look like. So here I have like 0 through 5. This might not always be a good set of points to plot. This might not give you like the full picture of the function. So it kind of comes with trial and error for like which points. The more points that you plot, the better. And if you plug these points in, if you plug 0 in, you'll get 0 squared minus 4 times 0 plus 4, so you get out of 4. If you plug 1 in, you get 1 squared minus 4 times 1 plus 4, so that'll give you 1, and so on. So you can see that this doesn't have a constant rate of change, because if I were to do 4 to 1, this is going down by 3. So the slope from 4 to 1 is negative 3. From 1 to 0, that slope is negative 1. This is like the change in output. Our change in input is just 1, right? So this is like plus 1, plus 1, plus 1. And then from 0 to 1, that's actually going to be plus 1. From here to here, it's plus 3, and then plus 5. So it does not have a constant rate of change, but what it does have is a constant acceleration. And you can see that from the differences of the slopes. So from negative 3 to negative 1, we're going up by 2. From negative 1 to positive 1, again, we are going up by 2. From positive 1 to positive 3, we go up by 2, and then we go up to 2 to 5. The next rate of change will be like plus 7. We'll get like a 16 over here. And so that this can actually kind of help you figure out like what the next couple values in your function are going to be. Like the next one will be 25 because we have to add 9 to the next one, and so on. Right? And if you plot all these points, it's going to look something like this. So you have this like arcing trajectory. The acceleration is like pulling you upwards. It's like positive 2. So sort of opposite